All right, sounds good. All right, hello everyone. My name is Brian Hentschel. I'm a graduate student at Harvard right now. So today I'm going to present on stacked filters, learning to filter by structure, which is work I did with Kyle Deeds, another member of the lab at Harvard, and my advisor Stratos, who many of you know. Cool. To get started, I'll start by explaining what filters are. Many of you probably already know this, but it's okay. Review is great. So the general idea people think of when they think of filters is that you have some data set, which we're going to call P, and this data set is distributed across a network or it's on disk, and you want to answer questions like is X in P or get X from P. In the naive solution is you just go to the data set and then get X and return it. But if you frequently have queries where X actually isn't in the data set, you can do a lot better by introducing a filter in front of the data set. So filters are very small data structures. They're generally designed to fit in cache or in memory. And they give probabilistic answers to this question of is X in P. In particular, they have no false negatives. So if the filter says something isn't in the data set, then it definitely isn't in the data set. But they have some false positives. So they can say X is in P, and then either X is in P, or maybe it's not in P. And generally, filters have a trade-off between their two main goals, which is that they want to be small, so they fit in cache or in memory, and they want to, and their other goal to produce as few false positives as possible. So for most filters, if you give them arbitrarily large space, they have 0 false positives. And if you give them arbitrarily little space, their false positive rate blows up towards 1, so that almost everything is returned as a yes, X is in P. Filters are used extensively in databases. Like one of their key examples is in LSM trees, where you have multiple levels of data. Usually data resides in one of your levels, but you don't know which, and you want to get that data item. So in this case, Bloom filters sit in front of each level and guard accesses to the level. So in this case, with high probability, you only go to the level where the data item actually resides and none of the other levels. And this is what makes LSM trees so efficient. For more complex examples that they can go way beyond just like is X in some data set, you can use it in probabilistic processing. So for instance, in web indexing and search, what actually happens is that a lot of the search terms get added into searches into a Bloom filter. So every web page has some filter which says like I contain all of these words, which might be hundreds or thousands, and then you query the Bloom filter for each page to see if it contains the terms that you actually have. If it doesn't contain those terms, you're done. Where if it does contain those terms, you send it to a machine learning model, which actually ranks the web page and returns like a ranking of the web pages to the user. And here, the filter is actually used to guard against sending things to a machine learning model. So it's another expensive process beyond just, is this thing on disk or over a network and get me. So these are just 2 use cases. There are many more, and filters are pretty ubiquitous. As I just said, they're used in web indexing and databases, but they're also used in financial transactions, genetics analysis, security, networking, and more. Cool. So with that said, we're going to go through prior filters. I generally think of prior filters as being in one of 2 camps. So they're either hash-based or they use classifiers, that is, they're machine learning based in some way. And we're going to go through an example of both. So Bloom filters, which are probably the most canonical hash-based filter, start with an array of bits, and all the bits are set to 0 initially. And then when you insert items, you hash this item some number of times, and you set the corresponding bits. So here you can see that dog points to 2 locations. You go from 0 to 1. And then you do this for every single item that's inserted into the Bloom filter, and let's say this is your final corresponding Bloom filter. Querying the Bloom filter uses the exact same hash functions, and then we'll check the exact same locations for the same key. So in this case, you query dog, you check certain locations. If all the bits that the locations hash to are set to 1, you return a yes. And so in particular, if the item was inserted into the actual filter, you're guaranteed to return a yes. So it satisfies the criteria of no false negatives. For items that aren't in the data set, you hash, and hopefully one of the locations has a 0, in which case you know for a fact that this item isn't in the data set, and you can reject it. And then a false positive occurs if by chance some item that isn't in the data set is hashed to all locations that contain set bits. In this case, you do have a false positive and you will think cat is in the data set, even though it isn't actually. Generally, I would say beyond Bloom filters, all of the hash-based structures use the uniformity of hashing to produce low false positive rates. So there's nothing inherent about the data or anything that you're querying. You're just assuming you have access to a hash function which generates arbitrary random values, and you use this to create low false positive rates. So this contrasts with classifier-based filters, which are going to try and use semantic meaning of the data to create lower false positive rates. So I'll use learned filters, which is the example that Tim Kraska gave 2 years back. So to start with, you take a set of keys, and then you also need to have a set of queries for non-keys, which you hope is representative of your actual workload. In this case, all the keys are animals, and in particular, they're mammals. As you would have, dog, rat, moose, mouse, goose. And then for non-keys, you have zebra, so some animal that's not in the data set, but then also maybe someone cares if Pedro is an animal, or you have like fire trucks, whatever it is that you think people will query that isn't actually in the data set. And because there is a semantic distinction, there's a hope that machine learning models can pick up on keys and non-keys and at least learn what is more likely to be a key versus what is more likely to not be a key. So after you have this machine learning model, you take each of the keys in the data set and you feed it through this machine learning model. For all the things that the machine learning model accepts, you're done. You're just going to go to the data set. For all the things that the machine learning model rejects, you have more work to do. And this is because if we were to just finish it here, you would reject keys in your data set, which would violate the property of filters that there's no false negatives. So every key that's rejected gets inserted into a backup filter. So then you're going to basically send all these rejected things to another filter and set bits inside there, or do whatever you need to do. And at first, this doesn't make a lot of intuitive sense. Like, why am I gaining anything if I'm, just using a filter at the end of the day anyway? But the answer comes that you have much fewer keys inserted to this filter. So if this classifier is accurate, you can have 1/10 or 1/100th of the keys you would have for a normal filter over nearly the same amount of space if your machine learning model is small. And so this makes it so that you have much lower false positive rates for that backup filter. Or alternatively, it can be very small and have similar false positive rates. So querying then follows the exact same path. You go through a machine learning model, you either accept it or reject it. And then if you're rejected, you go to this backup filter. And then learned filters have two places where false positives occur. The first is that the machine learning model can just accept something, even though it wasn't actually a key, in which case it produces a false positive. Or the second is that the machine learning model can correctly reject a negative, but then you can happen to have a collision when you query the backup filter, and then you have a false positive there as well. Hopefully, these are both very improbable. The first, hopefully, because the classifier is accurate, and the second, hopefully, because this backup filter has very few elements. And so if the classifier is accurate, both of these conditions can be met, and you can end up having a better false positive rate size trade-off than you would with traditional. So I think the positives and the negatives of both of these two approaches. The hash-based filters have a huge positive and there's no workload knowledge needed, so they can just use the keys in the data set. They're very fast computationally because you just need to hash things. And they're robust because they didn't use any properties of the negative queries. So essentially any workload changes aren't really a problem because you never really took the workload into account in the first place. And then their huge negative is that they're worse at, like the key goal that filters have, which is that they have a worse false positive rate size trade-off. And then if you look at classifier-based filters, these are essentially just reversed. They require workload knowledge, they're not robust, and they can be extremely slow. For many of the use cases that you want to filter for, you're going to need something like text processing, which generally requires a recurrent neural network or something similar. And this requires just a lot of computation, and it is tremendously slower compared to just computing 5 hash functions. But they do tend to have much better false positive rate size trade-offs. So what we're going to do is create stacked filters, which hopefully blends a lot of the better properties of both. Stacked filters is still going to require workload knowledge. So this is going to be its major trade-off. You're going to need to collect negative queries, but it's going to be able to achieve that better false positive rate size trade-off while being very fast computationally and while being robust to changing workloads. And this is generally because stacked filters are going to use hash-based filters in their construction. And this is what's going to make them have all these efficiency properties. Cool. So let's start with an overview. So to think about stacked filters, I think it helps to have this view of what a filter does. Instead of thinking about false positives and negatives, I want you to think of a filter as saying that an item is certainly in the complement of some set, so that it is not in the set, or you just don't know this item's membership. So it either could be in the set or not in the set. And the reason we're going to think of it this way is that we're actually going to recursively stack filters and use this to prune the set of items in the universe whose membership status is unknown. So we're going to be more and more certain about more and more items as we go down some stack. As an input to the stacked filter, we have two things, which are the positives and some set of frequently queried negative values. We'll talk about how to get these negative values later. And these are the two things that are observed and given as input to the stacked filter. The thing that is unobserved, but which is very notationally convenient, is to just refer to all the other negatives. And so we're going to refer to this as NU, the unobserved negatives. And just again, we don't actually need to observe NU, it's just a notational variable. And then the goal is to create the best filter with respect to some size constraints. So you want to lower the FPR and you want to be under some size budget. And generally these size budgets are going to be in bits per element so that they're allowed to scale with the size of the set. Okay, so before you've constructed anything, you can think of this universe of elements. So there's some items that are positives, some items that are frequently queried negatives, and some items that are unobserved negatives. And we don't know anything about any one of these sets before we see any filters. And they're going to construct this stack of filters. Each filter is a traditional hash-based filter, and you can think of them as Bloom filters here if you want, or you can replace them with cuckoo filters or whatever your favorite hash-based filter is. And L1, which is the first filter in the stack, or layer 1, stores the full positive set. So that is basically exactly the same as a traditional Bloom filter. And what this first layer tells you is that many, many items are not in the positive set. So you can eliminate a lot of unobserved negatives, and you can observe a lot of frequently queried negatives. And if we just finished here, we'd be done and we'd have exactly a hash-based filter. But what we're going to do is take advantage of the fact that we've collected these frequently queried negatives, and we're going to pass them on to some second filter that we construct using the false positives from your frequently queried negative set. And you can easily do this during construction just because you've stored these things, you feed them through the first filter, and you record the false positives. This second filter, L2, can tell you that things are not in the frequently queried negative set. You don't know whether they're unobserved negatives or positives, and because you can't have false negatives, the full stacked filter is going to accept any item that the second layer rejects. And I'm just going to say that again because it can get very notational, like very confusing in terms of reject and accept. These negative layers, which store things from the frequently queried negative sets, if they reject an item, the overall structure accepts that item and thinks it's in the set. So you can see here, this is a bunch of positives that get accepted and some unobserved negatives which get accepted. Finally, we pass the set of positives that were false negatives on this second layer to a third layer. And then this filter stores the positives there. And then essentially queries are going to work the same way. If they make it through that second layer, then they get queried against this third layer, which stores the positives. So why does this work and why does this have no false negatives? If you're positive, you definitely make it through L1. Then you go to L2, and if you're rejected by L2, you're accepted, so you're done and you can go to the set. And if you're falsely accepted, you get put into the construction of L3, and so you're going to make it through L3. So there's no false negatives. For things from our frequently queried negative set, if you make it through L1, you're in the construction set for L2, and therefore you get passed on to L3 and you go through a second check. So this is basically going to exponentially decrease your false positive rate. And then for unobserved negatives, you're going to have high possibility of being rejected at any layer. So the majority of rejects will come from L1, and the majority of false positives will come from L2, but essentially just because you act like something from P or NF, you do have decreasing returns in both directions. But I generally think of any unobserved negatives as basically having the same false positive rate as your first filter. So let's compare a single filter with this stack of filters. And if you think of a single filter, here we're going to say it has 10 bits per element, and then its false positive rate is 1%. And this is going to be true for each layer. So that would be the metrics if you just finished at the end of a first layer. Here's what's going to happen if you build two more. So you're going to have two sets, which basically and they're going to have size of 1% of your negative set and 1% of your positive set times the size of the filter. And in particular, if NF and P are about equal, this is about a 2% higher space. But your false positive rate on that frequently queried negative sets is going to multiply together, right? So it goes from 0.01 to 10 to the negative fourth. And this is a huge increase. And then the FPR and U is essentially unchanged. And so you can kind of see that there's a big gap in the things that you're trading off. Your size is growing extremely slowly, where your FPR on some negative set that you care about is decreasing very quickly towards zero. And this is the core intuition of stacked filters. Cool. So now to get a little bit less abstract and just to give a working example, we're going to go through this with Bloom filters, one hash function each for simplicity, and some actual items. And you'll just kind of a sanity check to make sure everything still works out. So we're going to have three items. We have three positives, three negatives, and you can see that we have three layers. The white ones are going to store positive elements. The gray ones are going to store negative elements. Okay, so you start by inserting the positive elements, and then you query the negative elements against the positive elements. The first two, by chance, happen to be false positives, so they get moved on to the next layer, where the third one is rejected, and you know that when you query it, you're going to be done. Then you move everything down a layer and repeat the process. The negatives are inserted, the positives are queried, and only the false positives from the positive set get sent on to this third filter. So then P1 goes to the third layer, you drop down the negatives, and you repeat the process. So P1 gets exerted, N1 and N2 get checked, and then N1 continues down. Stacked filters can be longer than 3 layers, and if you want to just continue the process, you just go on in this exact manner. The negatives get inserted and the positives queried, vice versa, and you do this on and on. One significant note is that you're always going to end with a positive layer, and that's just so that you don't have any false negatives. You always want to make sure that you're ending with a positive layer that catches all the positives. Cool, and then querying works very similarly. The positive goes to the first layer. It will assuredly pass through the first layer and then go to the second layer. If it's a false positive for the second layer, it goes on to the third layer. And because it was inserted there when we constructed the thing, it's going to be accepted. For N2, which is a known frequently queried negative, it was in our negative set. It goes through the first filter. If it's a false positive, it was inserted into the second filter, so it goes through, and then the second check actually catches that it's not in the set, and so eventually it's rejected. And then for N4 and N5, which are unobserved negatives, they can be rejected by either layer. So if the first one goes through this first layer, it's a false positive, hits the second layer, it's rejected by the negative layer, so again, it's accepted by the overall stack. And then for N5, it just goes to the first layer and is rejected like usual, and it's done. And so you can see both that this is correct, and in general, it's going to reject a much higher portion of these frequently queried negatives. So going on to the key metrics for stacked filters, we had this thing, which is we had exponentially decreasing sizes for each layer, and then we were multiplying together the false positive rates for these frequently queried negatives. And this can, to abstract a little bit from, this like size of 10 bits per element and 1% false positive rates, we're going to use the terms S of alpha and alpha. So S of alpha is the size function for the specific filter you're using. So Bloom filters, for instance, have like S alpha equals negative ln of alpha over, log 2 squared. And so this is basically just a way to go from the false positive rate of a single filter to its actual size. And then the false positive rate itself is alpha. And so this gives us the size of each layer. And then the false positive rate on the frequently queried negative set is just going to multiply. And then we can continue this down to F4 and F5. And then for mathematical convenience, it's going to be very nice to think about an infinite stack of these stacked filters. We're never actually going to build this infinite stack, but it makes the equations very easy to read and the metrics very nice. So if you look at it for an infinite stack, what happens is that this size becomes geometric series terms. So you have the size of a single filter with that false positive rate alpha. Then this first term, 1 over 1 minus alpha. Sorry, one more thing I should say is that this is size in bits per positive element. So I think that's generally the thing that people care about. We don't consider negative elements as part of the data set. So that's how we normalize by this P factor. So it's going to drop out of all the positive layers, and all the negative layers are going to be the size of the frequently queried negative set over the set of the size, over the size of the set of the positives. So you have the size of a single filter. Then this first term is a simple geometric series. So it's 1 plus alpha squared plus alpha cubed onto infinity. And then the second thing is that NF over P term and another geometric series, but starting with alpha to the first instead of alpha to the 0. So it becomes alpha over 1 minus alpha. And generally, because alpha is really small, this is 0.01 or something similar, this first term is going to be insanely close to 1. And then if your negative set is even close to the size of your positive set, this will again be something like 1%, or even if you choose a negative set that is 10 times as large as your positive set, this is only another 10% or something. So this only adds a little bit in terms of size. And then the FPR basically just goes to 0. Eventually, every frequently queried negative will be rejected. For the metrics for unobserved negatives, the end result is that the false positive rate is alpha over 1 plus alpha, which is very close to just alpha, the first layer in the stack. And then computation ends up working very similarly to some of the size things. So for positives, it's going to make it through the first layer with certainty, but then it's going to be rejected with high probability at layer 2. And then if it makes it through that, goes into the third layer, makes it through with certainty, rejected in the fourth layer with high probability. And so basically you have 2 times some geometric series, and the result is essentially an expectation close to just querying 2 filters. And then for negatives, essentially it's the same story, but starting at the first layer. And so you have 2 geometric series, which are very close to just 1. So you have almost no hit in terms of querying negative values in their computation. And the overall takeaway, I think, from stacked filters is that the FPR on some set you care about decreases exponentially so that you can just think of it as 0, where all of the negative metrics rise like geometric series. So they rise very, very slowly as the stack gets bigger and bigger. There are, and then we're also going to introduce a new variable and talk about stacked filters more holistically, which is that if you introduce this variable psi, which basically says, if I have a negative query, what's the probability it's in my frequently queried negative set versus my unobserved negative set, then you can think of the FPR as 1 minus psi times this false positive rate for the unobserved negatives. Generally, I think it's easiest to think about stacked filters as being of infinite length, and every filter has the same false positive rate, at least because this makes it so much easier to read the equations and to intuit when stacked filters are going to work. You can remove, obviously, both these assumptions. The filters are going to be finite in length in general anyway, and they don't have to have the same FPR on every layer. And if you remove both of those assumptions, you get these horrendously ugly equations, which I'm not going to go through, but you can read if you want. The main thing to note is that they're just modifications of geometric series. So if you look at this EFPR, or exponential terms. So this, is still just the multiplication of the false positive rates of every layer, every positive layer, and this is the false positive rate for your frequently queried negatives. Or if you look at computation, this is just a geometric series, but now no longer every term is alpha. It's alpha I and can be distinct. But otherwise, these metrics are the same. Cool. So now I want to close the loop. This kind of explained how stacked filters work as a structure, but we actually need to figure out how to, tune them. What are the size of the layers? What are the negative sets we're going to use? I'm going to go over this very briefly, just for time's sake. Yeah, but if you want to, you can read more in the paper. So in terms of workload knowledge, I would say there's 3 distinct scenarios. One, sometimes you get lucky in that there's just publicly available knowledge. So we're going to see this later when we look at URL blacklisting, where the negative set for URL blacklisting is just web pages that are frequently queried. In this case, Alexa, which keeps a free open source database of what the most popular web pages are, and you can just download this, as well as the query frequencies for all web pages. The second thing is that they can be collected by default. So Google for web indexing basically logs every single search that someone does, and so you can have right at your disposal what people are searching. And then the third, and this is probably the most likely for databases, is that you collect them by choice. So you have to go out and basically say, trace this workload for a little bit. Here's my negative set. In terms of optimization, it's going to work in a couple steps. So the first is that you model the workload. This is basically in the idea that you are in 2 or 3 where someone hasn't already done the analysis for you. And you essentially just collect past queries, form a histogram, and then you can take, the n most popular items, you have their query frequencies, and you can use a bootstrap estimator to estimate the number of queries of elements which are not seen in your query sample. The second thing you can do is then, sort the items from most popular to least popular. It's always going to be, the best solution is a greedy solution. You will always want more popular items over less popular items. And there's a way to do this such that you only check certain values of your frequently queried negative set size without really deviating from the optimal stacked filter. And then the third thing is that you optimize once you fix that frequently queried negative set and psi, which is the proportion of queries aimed at that. And then there are 2 distinct scenarios here, which is you have continuous FPR filters, which I think of as Bloom filters. They can basically take any false positive rate you want. Or you have discrete FPR filters, which are things like cuckoo filters, where the false positive rates have to be some power of 2. And for these, they're going to be optimized slightly differently. Yeah, so for model workload, here's basically the output you would generally see. So you see some past query logs, you see the terms, you see what proportion of queries you think are aimed at each thing, and then you have some unseen value, which basically says, oh, I actually think 15% of queries are outside of anything in this set. You would sort them, and then you're going to be able to this approximation to the best stacked filter, where you only need to check certain locations. So you can know after the first item, after the third item, after the 7th item. Although, with millions of elements, they'll obviously be much farther spread apart. And then finally, you can optimize with this fixed set of NF and psi. For the continuous FPR case, what we're going to do is we're going to fix the FPR across layers. And in this case, the equations become what's known as quasi-convex. So they're not convex, which is generally like smooth shapes, but they do have unique local minimum. So you can solve this by gradient descent, and then you just generally truncate to some small number of layers. And this actually works very well in practice just because the things converge so quickly. There's something like alpha, which is 0.01 to, like the 5th and then the 7th and then the 9th power. These are going to go to insanely small values insanely quickly. And then for discrete FPR filters, you can actually just use a variant of breadth first search. And this is because, again, for cuckoo filters, the FPR rates generally have to be a power of 2. So they're something like 1/2, 1/4, 1/8, 1/16, and you can just check these at each level in a smart way. The result is that for both, you can find a filter which is arbitrarily close to optimal under the assumptions that you've made. So the continuous FBR case, we assumed that alpha was fixed across layers. We can get arbitrarily close to the optimal, and it takes time of O of epsilon to the -1, where epsilon is this slack we're allowing from like the theoretical best thing we could create versus the actual thing we found. For discrete FBR filters, we allow any value of alpha possible. So this is any possible stack filter you could make. And again, we give the same guarantee, but we require time O of epsilon to the -3. Cool. So now we're going to go through what I call theory experiments. These are basically just going to tell you when our stacked filter is better than regular filters and by how much. And they're just going to rely on summary properties of the data. So you don't actually need a full data set to do comparisons. The one prerequisite I'm going to say is that we require that S of alpha be in this functional form. So this is -log2 of alpha plus C over F. This is true for all filters I've ever seen in practice, and the actual theoretical lower bound for hash-based filters is just -log2 of alpha. So this also holds true for whatever the best theoretical filter is. So I think this is a safe assumption to make. The first, we have theories that says when are stacked filters strictly better. So without going into it, this is the theory. And then by how much are they better? Because we have quasi-convex optimization problems, you can actually quickly solve for the best value of alpha and then essentially say how much better are we than a single stacked or single hash-based filter optimally tuned. And for both of these theories, the main thing to note is they rely only on two values, which is this relationship between NF, your frequently queried negative set, and how often that frequently queried negative set is queried. And then using these theorems, we can basically create nice visualizations, which allow us to see what's happening. So this is the first thing we're going to see. So what we're going to have is on the bottom, we have a ratio of the size of our frequently queried negative set to the size of our positive set. And then on the y-axis, we have what proportion of queries do we need to be at the frequently queried negative set for it to be better to use a stacked filter in terms of FPR versus size specifically, not counting computation, versus just using a single hash-based filter. And here's the cutoff. So you can see that this is at a false positive rate of 0.3 that is desired. And there's some very reasonable use cases that I think fit into this. So if you have a negative set that is half the size of your positive set, you only need something like 15 or 20% of your queries to be aimed at this set for it to be better in practice. And then, the larger your negative set, the more you need things to be aimed at the thing in the negative set. If we want more hash values or more desired false positive rates, we can graph them multiple times. So this is a 5%, 3%, 1%, and 0.1%. You can see that as false positive rates drop, it becomes easier and easier to find workloads that match stacked filters. In particular, I think basically by the time you have a false positive rate of 0.1%, I would argue that there's essentially no workload in the universe that doesn't meet the criteria. Like your positive set is entirely as big as your positive set, and you need to have something like 1% or less of your queries to be aimed at this to be better. The next thing that you can ask is not only when are stacked filters better, but how much are they better by? And then here is another graph where we took those same lines, which are these lines, and we graphed them, and then we graphed kind of different values of workloads and put them against the things needed. So these lines show how much of the queries are aimed at the most popular elements for a couple of workloads. This is a uniform workload with 10 million, with the negative set that's 10 times as big as the positive set, and then 3 Zipf-ian distributions with basically low skew, high skew, and very high skew. And you can see, just generally the more skewed the workload, stacked filters do better and better, but that even under uniform workloads, which are insanely bad for stack filter, you're saying that there's no frequently queried negative elements, that oftentimes this line will actually pass the desired threshold. And it's still better to use stacked filters than if you were to use just a traditional single hash-based filter. The other way you can dice it is you can see, like how much space savings am I achieving for the same false positive rate at some, set i's for my frequently queried negative set over my positive set. So you can see again that now we're making the negative set bigger and bigger as we drop down the graph, and we're increasing the psi we've actually achieved with this frequently queried negative set. And you can see essentially the space savings. So under extreme scenarios where you get something like 90% of your queries at a frequently queried negative set, you can basically reduce the bits saved from something, like 10 bits per element for a Bloom filter down to 4 bits per element. So this is a pretty big space savings. We're cutting the space required essentially in half. And then as that frequently queried negative set gets bigger and bigger, your space savings get smaller and smaller. Cool. And then so for actual experiments, how am I on time, by the way, Pedro?
Yeah, I mean, if you can finish it up in 5 minutes, that would be pretty on time, I would say. Then we have like 15 minutes for questions.
Perfect. So for experiments, the first thing we're going to show is URL blacklisting. So this is actually the same exact experiment that Tim Kraska and Google did in introducing learned filters. The basic idea is you have some positive set, which are spam URLs. In this case, we have 2.8 million URLs, which are half pornographic, half non-pornographic. And your negative set is the negative set we use is the most frequently queried web pages. So, Google, Facebook, ... in order, and the full top 10 million of them. I don't know what the 10 millionth most visited website is, but it's in there. And then the query frequencies are proportional to the page rank. So Google is the most frequently queried web page, and ... And then for learning, both learned and stacked filters are given the top 5 million URLs, and then the bottom 5 million URLs are basically allowed to be whatever they're not given to either stacked filters or learned filters. And learned filters for training, and stacked filters for the size of the frequently queried negative set. One of the things that I should also mention is that stacked filters is given the 5 million URLs to choose from in terms of its optimization, but it's not actually required to use all 5 million URLs in the actual structure. It can choose to use 3 million or 2 million if it wants. And then for the hardware, for all the hash-based filters, we're using a Intel CPU, whereas for learned filters, we're actually also giving it a much better hardware setup. We're basically giving it the CPU plus a GPU. So knowing, neural networks, this is very important, or otherwise all the comparisons in terms of computation would be even more skewed than they already are. Cool. So in terms of false positive rates for size, blue is the stacked filter, green is the learned filters, and then the query agnostic filter, which you can think of as, in this case, I think it's a Bloom filter, is the dotted orange line. And you can see that as desired, the blue line is, much, much lower than the query agnostic filter. And then once you get to about 6 bits per element, it's also lower than the learned filter. And then for less than 6 bits per element, it's pretty close. So I would say that these are fairly close false positive rates. There's some gap because this is a log scale, but either way, these are both pretty close. And then there's a clear winner is stacked filters as you have more and more space. In terms of computation, the graph is almost level. So you can see that stacked filters is very close to query agnostic filters, hash-based filters. The negatives are essentially identical. The positives are about 2x, which makes sense given our analysis. And then the learned filters using the GPU are something like 1,000 times slower. So they actually go off the graph, and we just gave them that they're taking 24, I think, microseconds in comparison to 0.13 microseconds. And this also makes sense given the GPU. And then if we look at kind of a more holistic thing of okay, well, if we combine together computing the things for the filter and then either going to SSD or hard drive for every false positive, what is the best filter? And you can see, and then each of the graphs is divided up into 2 parts of the bar. The lighter color is the computation time, and the darker color is the time that's spent going to disk. And you can see essentially that the stacked filter is always the lowest. Depending on the false positive rate, the query agnostic filter and the learn filter trade off. At very low false positive rates, there's just a ton of disk accesses, so the query agnostic filter can decrease. And then as you get lower and lower false positive rates, just this computation time for the learn filter will kill you, even for hard drives. And then if you're accessing an SSD instead of a hard drive, essentially the computation for learn filters makes it that it's just never going to compete. Like, it's too expensive to calculate these GPU things. We repeated this for multiple other data sets. Firehose, which is a networking benchmark, which shows a lot of the same trends. The only thing is that in this case, learn filters wasn't really able to pick up on any pattern inside the data set, and so performs worse than just even a query agnostic filter, whereas stack filters can just memorize things. And then the rest of it is essentially identical. And you can see that for some of these, we're actually way, way better than any competition. So I think it's like 96x better in terms of Firehose, which is a very skewed data set in the best case. Yeah, and then the synthetic data set basically shows it Zipf-ian distributions with more and more skew. How does stack filters compare to query agnostic filters and learn filters? And in this case, because the data set is synthetic, I will say that like it's not really possible for learn filters to learn anything here, but reviewers asked for it, so there it is. Yeah, but you can see the same pattern. The stack filter is better. It's better, or it's approximately the same on computation. And then generally, if you're guarding against anything that's expensive enough, the stack filter is going to have the best overall performance. Cool. Now I'm done.
Thank you very much for accepting our invitation to give a talk. I think we have a bit more than 10 minutes for questions, so whoever wants to be the first one.
I should probably show this. Yeah, go for it.
Should I start?
Yeah.
Right. So one question, correct me if I'm wrong on this, but the stack filters, they don't differentiate within the negative set, right? So every element has kind of the same weight, correct?
You mean every element in the frequently queried negative set?
Yeah, exactly.
Yes, yeah, totally.
Because I can imagine that when you consider, for example, this blacklist, like you said, Google is much more important to get right than the 10 millionth most accessed website, right? Because there's like an order difference of probably 100,000 in terms of like how frequently this is accessed. So, but I think it's probably maybe something interesting as well to look at.
Yeah. Yeah, I agree. It is interesting. And we thought about this. We couldn't find a way to exactly capitalize on it. So that'd be great.
So the next paper is weighted stacked filters.
Yeah.
Another question, of course, since your supervisor is Stratos, have you thought of a way of building these things adaptively?
Yeah. So in my opinion, it's semi-adaptively, but the answer is yes to some extent. So I would say that there's two parts of stacked filters. There's this like optimization, and then there's the actual building of stacked filters. So it's the optimization, I think, is the tricky part. Like before you see data, or like how can you do analysis of a workload on the fly? And I think that this is extremely difficult. But if you can make good assumptions, then you're fine. And you don't, the thing that's good is you don't actually need this frequently queried negative set in advance. So one of the things you can do is basically you build this first filter, and then as negatives come in, you basically say any negative that's a false positive on my first layer, just insert it into my second layer for some number of elements. And then you stop when this second filter is, quote, like full enough. So, you know, for a Bloom filter, this might be when like half your bits are set or something like that. Or you can keep a counter and just say, I did this 1,000 times for Gucci. And then after you've constructed this second set, you will need to do something which is painful, which is you need to read in that positive set again, but you can then feed in the positive set and construct this third layer as usual. So that's kind of a way to collect the actual frequently queried negatives on the fly. The thing is, you just need to figure out, you know, how big should these filters be? And I think as long as you have any even like guess of how the workload is, I think that's fine because if we looked at kind of these theory graphs, like things mostly work out pretty well as long as like the psi is somewhere, you know, like you don't need to know the value exactly. But it's difficult to talk about in the abstract because I think you kind of need to have at least a rough sense of how your workload is. If you know nothing about it, I would say it's very hard to do this on the fly.
Well, you could argue or like intuitively argue that if the frequently requested items are actually frequently requested, you're probably going to see them in the first 100,000 entries or something, at least the very, very frequent ones. So
yeah,
it could in practice work, but theoretical analysis of this is, I would guess, impossible because it depends on the workload.
Yeah, completely. I agree.
Well, very interesting stuff. Thank you.
Okay, I have a question. First, a clarification question. Are all the bit vectors equal size on all the levels?
Say that one more time.
Are the bit vectors on equal size on all the levels?
No, so generally the bit vectors will decrease very, very, very quickly.
Okay, fine. Did you compare actually what the effect is of merging actually all the space into one bit vector on the top? So take the total space of the which you allocate for the bit vectors and compare what will happen if you then apply any of the known structures. So because I could be the devil's advocate and say, okay, if I take the bit vector on level 1 and level 2 and knit them together, I have a larger bit vector, my Bloom filter will be better anyway.
Yeah, so that's essentially what we're doing. So whenever we have, for instance, performance graphs, like in our experiments, this top line is essentially exactly that. So if we gave the Bloom filter the same amount of space as we're giving all of the levels in the stacked filter, then that's the performance we would get.
Okay, thank you. That's a good clarification.
Ryan, can I ask a question? I hope my internet is good enough for a question. I had some problems. Hey, so interesting work. Now, of course, in the group at Harvard, you have a keen interest in all kinds of indexing structures that consist of multiple parts, like LSM kind of flavors. And in those, as you said in the introduction, filters are used a lot because if the query comes, you want to avoid searching a particular piece of such an LSM style index. So I mean, you must have thought about it, but that's my question. Did you think about how this ID plays into those structures? Because in a way, very often what you will have is, okay, now you have to say, okay, we need workload information. And having workload information is nice, of course, if you have it, but very often it's hard to come by or you don't have it yet, you know, so.
Yeah.
Anyway, but in the case of an LSM kind of like family and an LSM family of data structure, you kind of do an idea of what those negatives are, you know, because if you are at level 1, then very typical your negatives is the stuff that's at level 2, 3, 4, 5, and 6. So have you thought about that? And in a way, I mean, you know, there is currently, I mean, if you would use straight Cuckoo or Bloom filters, you have multiple filters like you have here. Of course, they are very differently sized, but you have the same situation. You actually have multiple vectors. But so how would your ID play into those structures? Would there be a special synergy or not?
Yeah. Okay. So I'll discuss, I think, first LSM trees, and then I kind of a couple of the other possible database use cases. So LSM trees is something we're kind of actively considering right now. And I think the core idea that you said is totally correct. You know, it's like the idea is that most of your false positives on these upper levels come from the lower levels. And, you know, like there's that very specific structure of like, things don't have to truly be negatives for the LSM tree in general. It'd be like false negatives on, false positives on layers. And one of the idea might be actually to kind of use some of the ideas that Mark brought up, which is that you can build this kind of incrementally. So maybe what you could do is you build this like you build these bloom filters, or your first filter as usual. You observe the negatives kind of in the background and build this second layer. And then there's this idea that, and it's not fully fleshed out, that then when you merge and send to the next level, you'll have these positive vectors and you'll have a negative vector, and you have to read in the positive set anyway to, you know, merge it for the next level. So you might be able to build the third layer at that point. You know, there's no workload analysis. I feel like statistics are a little hard to come by in RocksDB and some of the other LSM trees, but if you know something about the workload, I think this is a strategy that might work.
Right.
And I'm talking a little bit to some of the members of my lab who know more about LSM trees than I do to see if it might work.
Well, there is a whole different dimension, of course, which is also typically neglected in LSM trees. Because usually LSM trees, they are kind of some workaround to the situation that you cannot really do update in place. So you end up with those like multiple structures that you want to rewrite only exponentially increasing times in order to amortize the whole updating business.
Another scenario that I thought about.
But to finish my sentence, these LSM trees, they do not take into account so much workload information, because there is an incentive to keep the most frequently accessed items in LSM trees in the top level, or the top levels, basically, which is currently not happening typically.
Right.
So in a way, there could be this synergy. So that was what I was kind of insinuating, both in terms of the accuracy of your filter to keep, for instance, track adaptively, like you say, of negatives. But then when reorganization time comes, you might actually use your information about negatives to steer, to kind of reorganize in a bit different way, you know, to not necessarily dump all the items in one field level into the next level, but maybe keep some of them. Or maybe even import some of the very frequently used negatives, which are basically the items that are stored in the next level, in top level, because they are so frequently queried. So maybe I'm thinking too far here. But you were also going to say something. I was interrupting you.
Yes, so actually another thing that like I think people in this lab group would know a lot about, and which I've considered as a possibility, is when you have something like joins, or in particular distributed joins. I know sometimes people use bloom filters as a filter before you hit the join. And in this case, you have access to this kind of natural negative set of like the things that don't qualify for a query. And in particular, I think it also works well in that like the size of the negative sets and the size of the positive sets are not going to be astronomically different in many situations. And because of the like equations, it's actually fine if this negative set is, you know, is 10 times as big as the positive set even. And so in this case, you can basically just say like, maybe I insert everything that doesn't qualify into my query as like part of the net frequently queried negative set and use it in, you know, some second layer. I don't know distributed joins well enough to know if this is exactly like a perfect use case, but it's one that I've considered might be a good possibility.
By the way, I didn't get this figure that you show here, because there are 4 different lines. No, this one. There are 4 different lines in 2 families of colors. But but how do they relate? You know?
Did you get
like no, the other one. The blue stuff. What distribution does it talk about?
So do you get this one?
Yeah.
Okay, so this one is like what psi do we need and like what's the size of the negative set to the positive set, right, for these false positive rates. So the blue lines are actually exactly the same. They haven't changed at all. This figure, what it's showing is basically the CDF achieved by the most popular elements.
But the blue stuff is uniform. Or what is it? What is the distribution of that?
So the blue stuff is
assuming a uniform frequency distribution of the queries, or what?
So there's no, okay, the blue lines they're kind of like distribution independent. So they're basically saying that any workload where it's like frequently queried negative set at, exactly the size of my positive set, if at least 20% of queries are aimed at that set, regardless of what the distribution is, as long as it has 20%, the stacked filter is going to be better. And then, as it drops, if for the 1% false positive rate, it says anything, with 10% of my queries at a frequently queried negative set that is allowed to be as big as my positive set, the stacked filter is going to be better. So that's kind of the workload independent analysis of the stacked filters. Then here, the green lines are the actual workloads. So right now what I'm taking is a zip at 4 levels, the uniform being z equals 0, really. And I'm basically saying if I have 10 million negative elements and 1 million positive elements, what is the CDF traced by the most popular items? So by the time you get to a negative set that is 25% of the size of your positive set, if you have a very skewed distribution, like a zip with z equals 1, this can actually be 80% of your queries are aimed at that, which is, way above the actual like break even point we needed of like 20% or 30%, or, even 5 or 10%. And then as you go larger and larger, you're just collecting more and more negatives. So it says, if I collect 1 million negatives from a zip with z equals 1, I'm at basically like 0.85 or 0.9. Or if it's z is 0.75, I've collected, 55% of queries are at that set. So it's basically just tracing workloads and how they fit according to these curves. And the yellow line is of interest because I think it's like the worst case. And here we're basically saying if there are 10 million negative elements, so that by the time I hit 1 million negative elements, 10% of the queries are hit. Even under this worst case scenario, this can actually pass, a single traditional filter. You can still do better just by collecting arbitrary random samples and adding them to your negative set than if you just did nothing.
Okay, guys, so we're slightly over time, but if someone else has one last question, feel free to shout. I guess that's a no then. Well, Brian, thank you very much for a very nice presentation and for taking the time to give it to us. And yeah, so I think we all wish you a lot of success in the end of your PhD.
Cool. Thanks, Pedro. Good to see you again.
Always good to see you.
Thanks, Brian. Very nice talk. Thank you.
Bye-bye.
Thank you. Bye.